Okay, good morning. Today we'll be talking about temperature sensors again, but this time we'll be talking about non-contact temperature measurement. So, how to measure temperature of an object which is distant from us, and how to estimate its temperature. Uh, we will be talking about infrared cameras and infrared thermometers. They both share the same principle. The most important thing is that when you are using non-contact temperature sensors, you are not measuring the temperature directly, but you measure radiation. And from the radiation, you will get an estimate about the temperature. So imagine we have an object and we would like to measure its temperature. We will be using Planck's law that relates temperature to radiation. And the temperature of the object is proportional, well, the radiation from the object is proportional to the temperature. And this will be measured in emitted radiation. So here we have the object, here we have the sensor. But unfortunately, there are other effects and other sources of radiation that we need to take into consideration as well. One source of radiation that will go directly to the sensor is ambient radiation. So this could be the sun, this could be the reflection from some other objects than the one that we measure. And the ambient radiation is going always to the sensor as well. So that's one component. Another component is reflected radiation. So we may have some source of radiation. This radiation is going to the object itself, and then it is reflected and is going to the sensor. So if we have some other sources around our object, then we may see the reflection. We have also a part so-called transmitted radiation. In cases where the object is transparent for infrared radiation, then if we have some source of radiation behind our object, then this may get through and we may see it as the temperature, but in fact it's not temperature of our object, it is the temperature of the objects that are behind. And we also have absorption. This is absorption in the atmosphere, and it's quite important, especially if you measure through long distances. So if this distance would be 10, 20, 100 meters or above that, you may get some portion of the infrared radiation absorbed in the atmosphere. We'll see also some charts that relate this further. So we have all those components. So we would like to measure only emitted radiation, but in fact we measure the sum of emitted radiation, reflected radiation, ambient radiation, and transmitted radiation, minus the absorption in the atmosphere. So when we will be working with this infrared devices, we will have to take this into consideration. We'll do some experiments with reflected radiation, and we will also see the effects of transmitted radiation here. So, regarding the emitted radiation, I'm sure that you have seen this chart in physics. It's Planck's law, and this chart is saying us how much radiation is radiated from an object with a given temperature. So here we have the amount of radiated energy. Here we have the wavelength, and this is the temperature in kelvins of the object that we study. Here you see 3500 Kelvin, 4000 and so on. 5500, that's roughly the temperature of the sun. And visible radiation is somewhere around here. So let's say 400 to 800 nanometers, 750. So what we see with our eye is somewhere in this band. So here, this wavelength, 650 nanometers, is red color, and we will also see one of the non-contact thermometers specifically working for 650 nanometers. It is visible that the warmer the object, the more blue it will appear. So here, if we see normal objects with, let's say, 300 kelvins, then they would have the peak somewhere around here, some very far in the infrared range. And only as the objects are getting hotter and hotter, and we see the glow with our own eyes, because this gets into the visible wavelength. So here, that's what we see. If we want to measure the temperature of objects that are in the range of 300, 400 kelvins, then we need to work in the far infrared range. So it's somewhere around this part behind this chart. The amount of radiation is proportional to the temperature of the object. So if, for example, I take one wavelength, then I can say, okay, if this amount of radiation is this one, then I have 3,500. If I have this radiation, then it's higher temperature. If I have this amount of radiation, it's this temperature, and so on. So there is a relation between the radiation that I measure and temperature. This is given by Planck's law, which is shown here. And what's interesting from this chart is that it allows us to estimate what wavelengths do we need to measure if we want to obtain the temperature of some object. Here you have a chart that is showing you 90% of emitted radiation, or the energy that you receive for a specific temperature of the object. So let's say we have an object with temperature 0 centigrade. So 90% from this curve are between 5 and, let's say, 30 micrometers. So it's a really far infrared range, and we'll see we'll need different optics and different materials for that. If, however, we want to measure object with 1000 centigrades, then 90% of the radiated energy is between, let's say, 1.5 and 10 micrometers. So we'll need different materials than for this section where we want to measure lower temperatures. We will need the definition from physics, and that's the definition of a black body. We will say that an ideal black body is an object that receives all the radiation, and it is also an ideal object that can transmit all the maximum amount of radiation. So here we have some radiation that's incoming on the black body, and we want that it radiates a maximum amount of energy. This is a fictional object. We can get quite close to the black body with some materials, but still not the ideal thing. And we will define the we will compare the black body behavior to the real object with something that is called emissivity. Here I have an idea, a table for you. It is saying what is the emissivity of given objects. So here you see ideal black body has emissivity 1, and all other materials have emissivity that's smaller than 1. For example, graphite or coal can get quite close to this ideal black body. You can see up to 0.97. Typically, we have objects that have 0.95. You will see that also in the lab. The other materials have lower emissivity. What is important in this table is that typically there is a really large range of emissivities. And when we will be doing infrared measurements with IR thermometers and IR cameras, if you want to read correctly the temperature of your object, you need to set exactly the correct emissivity. We'll see also what will happen if we don't do that. So here there is a really large range of emissivities, and this is one of the biggest issue when you are doing infrared measurements. It is that you don't know the emissivity of your object, so then you can't read the absolute temperature from the object. One interesting thing is a sun, a black body object. Well, almost. And the almost you can see over here. This chart is again the Planck's law. It's of the sun. And here this black curve corresponds to the black body object that has the same temperature. So the sun has temperature 5250 centigrades, and this would be the curve from the Planck's law. The real solar spectrum is shown here in the yellow color. So you see that at some points we are above the radiation that would correspond to the black body. So especially here in the visible spectrum, those peaks are higher than it would correspond to Planck's law. On the other hand, here at this area and in this area, we have a lower amount of energy that would correspond to the black body. The reason is that the sun is not one object composed from one material, and here it radiates a little bit more, here it radiates a little bit less. The yellow is on top of the atmosphere. The red color here is the radiation at sea level. So here we can see the absorption in the atmosphere. All this is absorbed in the atmosphere, and here we can see individual components responsible for that. So here oxygen, water, and carbon dioxide. So this demonstrates us that if we would like to measure the temperature for long distances, we need to take absorption into consideration, because otherwise I would read a different temperature than would correspond to reality. Another thing is that the black body is an ideal object, and it is defined for objects that are much larger than the wavelength of the radiation. So if you would like to measure the temperature of, for example, small particles like dust that you have in the atmosphere, then you will find out that emissivity of those particles is much larger than 1. So it would seem like it is better than the black body object. The reason is that if you have a small particle compared to the wavelength of the radiation, then you can imagine, okay, it's like a flow of the energy. But if the particle is about the same size like the radiation wavelength, then this happens. So it looks like this is the particle, and this is the radiation, and it looks like the particle has a larger area than it has in reality, because it's influencing the electromagnetic field around it. So for small particles, it's not true. You cannot measure that without any changes with infrared thermometers, because you would have to set emissivity larger than 1. Something more for the atmosphere. If we measure in the atmosphere, then we have to use wavelengths that are not absorbed as much as other wavelengths. So here we have 3 so-called window: short wavelength, large wavelength, and medium and large, long. And here you can see, okay, this is the wavelength, and this is the absorption in the atmosphere. So if I would measure for some reason in this wavelength, for example, then all my radiation will be absorbed, and I could not measure anything in the atmosphere. I need to choose the wavelengths that are not absorbed as much. So here we have the one window from 8 to 12 micrometers. There will be some materials good for this wavelengths. There will be other materials good for those wavelengths from let's say short infrared and up to 2.8 micrometers. Again, here you can see the materials. So this gets absorbed in water, this gets absorbed in oxygen, and so forth. It's true also for larger wavelengths. So here you see the same chart all the way to 70 micrometers, and here it gets absorbed and scattered. So here we cannot measure in the atmosphere directly. We simply can't do that. Okay, so now let's take a look on some materials that are good for infrared optics. This is just for illustration. I'd like to show you that materials for infrared cameras and infrared thermometers are completely different than standard optical materials that you can find in cameras that you probably know. So here we can see some components. This is the wavelength, and this is the so-called detectivity. It's the ability of the detector to detect the incoming radiation. And here you see, okay, for example, if I select, let's say I want to select germanium, so this material, and if I use this material, if I want to use it, I can use it only in this wavelength. So between, let's say, 500 nanometers to roughly 2 micrometers. So if I would need to measure in this range, I will select this material. If I would like to measure in the range from, let's say, from 5 to 13 micrometers, then I would need to select this material. If you look on the front side of the thermal camera, which I would like to show you here, then I'll pass it a little bit later. Look on the material of the lens, and it's definitely not glass. So those thermal cameras are typically made either from germanium or from silicon. For example, here you see an alloy of silicon and gallium has a quite nice characteristic from 6 to 17 micrometers. Here, for example, those materials are used for solar panels. So they just give you an idea what materials are used. Here we see one interesting thing, thermistor and barometer. So you see it has a quite nice characteristic from 1 to 17 micrometers. But if you compare that to the different materials, to the other materials, you see that the detectivity is much larger. So a few orders of magnitude smaller. So here, okay, a thermistor is a really nice sensor for infrared radiation, but it has a really small sensitivity. If I want something more sensitive, I definitely need to take those materials. By the way, here you can see also the dependence of temperature on the detectivity of the material. So here you can see if I have a germanium detector cooled down to 77 kelvins, then it has about this sensitivity. It's very sensitive. But if I cool it only to 196 Kelvin, then I have roughly one order of magnitude smaller detectivity. So the best detectors that we can have are cooled with liquid nitrogen or even to lower temperatures. Here is roughly the same thing, but it shows the materials that are used for optics, for infrared cameras and infrared thermometers. Normal glass is somewhere around here. We can see through normal glass, and we can the radiation can pass through that. If we would like to work in the infrared range, you can see, for example, germanium and silicon are used for the lenses in this range. If we would have the other material like sodium chloride, then it's partly transparent for UV, for visible, and also for infrared radiation. Sodium chloride, it's salt, so it would not be very good for the reliability of the optics, but as an optical material, it looks quite good. So here I have some examples of materials, and we will see how this affects the radiation. So here I have some samples, glass and other materials as well. I have here a thermal camera, and I'll try to show you the image from that so that we see what is happening. I had some trouble in installing the device so that you can see the picture. So I really hope it will work. Well, it's still installing something. So let me continue, and then I'll come back when this works. So we'll start not with the IR camera, but we'll start with the IR thermometers. And I'll show you one thermometer that is good for high temperature readings. This thermometer is the so-called disappearing filament thermometer. You have the chance to work with that in a lab. So how does it work? We know that the amount of radiation that we receive corresponds to temperature. And if you look on the Planck's law, which is shown again here, then if I would look on single wavelength, let's say 650 nanometers, and I can look on the intensity of the radiation, then I can relate that to temperature. So the principle of the disappearing filament pyrometer is the following. We have an hot object. The radiation is focused from a lens. Eventually it's going through a filter that will decrease the radiation so that we can look directly into on the object. It could be an oven, for example, where we melt glass or where we melt some metals. And then we have a lamp, and in this lamp there is a filament. So it's like a bulb. And we compare the brightness from the object with the brightness of the filament in the bulb. And we look with our eye on that, and we compare the brightness here and the brightness over there. So what we see typically looks like this. If the object is hotter than the filament, then the object has higher brightness and the filament is darker. So we see something like this. So this is the background, that's the object, and this is the filament. So it looks like a black line on a bright background. So now we know that the temperature of the filament is smaller than the temperature of the object. Here we have an opposite situation. We have a hot filament and its temperature is higher than the temperature of the object. So here we see a bright filament on a little bit less bright background. And the goal that we want is, I should have shown it here. So this is the hot filament on a little bit smaller brightness on the background, and here we have the hot filament, and the temperature of the filament and of the background is the same. So here we know, okay, now we have the same temperatures. And on the pyrometer, you can adjust the brightness of the bulb simply by changing the current. So here you have an example of this device. So this is where you look on the object itself. Here you have a scale that is calibrated in temperature, so centigrades, for example. And the bulb is inside. You look through this eyepiece, and by turning here the knob, that's this black thing, you change the brightness, and then when you're satisfied, when you don't see anymore the filament, then you simply read the scale, the value from the scale, and you read the temperature. So the filament disappears from your view, and that's why it's called disappearing filament pyrometer. So here, this is the situation that we want. This is a device, an instrument that requires our eyes, requires our interaction, so that we can adjust the current. In automated devices, we want to read the temperature directly, so we need to eliminate the human presence, and therefore we can use something like this, the total radiation pyrometer. The function is similar, but here instead of our eyes we have a temperature sensor. So it's a temperature detector. Typically it's a thermocouple, because a thermocouple has a small time constant, so it can react quickly to the changes of temperature. So here we have the object with temperature that we want to measure, emitted radiation from the object, some lenses. Here we may have also a gray filter that decreases the amount of radiation, and now this is focused on the temperature sensor, and here we eventually may also look with our eyes on the object, but it's not required here for the function of the sensor. We can read directly the temperature from the temperature sensor, and it's clear that when this object will be warmer, then radiation will be larger, and here the temperature will be higher. So this is calibrated directly in centigrades, and we will read the temperature from the object. Let's see if the thermal camera is already working. Okay, it seems to be finished, so I really hope that it will work. So I'll try to show the picture from the thermal camera. It doesn't seem to work at all. So for some reason it does not see the thermal camera. I don't know why. Oh yes, this keeps opening the camera in my computer. Okay, so we'll do it in a different way. Uh, I'll have to use this one. Okay, so we'll do it in a different way. It's not working. So I'll pass you this thermal camera so that you can play yourself with that. Here there are different objects. Well, probably will be. I'm not sure if you will be able to see that. Do you see a little bit of the screen? I'll pass you the materials later. So now it's a thermal image, and the glass should be blocking the part of the heat from my hand. So you should see my hand, and then it's cut from the glass. Those materials like this plexiglass, they do not block that much the infrared radiation, so this will be fine. Here I have some plastic material, polypropylene, and you see the hand is now clearly visible in the box. So even this material blocks visible light, it does not block infrared light. And what I was hoping to show you was reflection. Here, this is the image from a thermal camera. You should now see your reflection, more or less. I really can't do that because I don't see what I'm doing right now. So yeah. Right now, you see, there are some people inside. That's your reflection, the reflection from the metal. So this acts as a mirror for infrared radiation, and I was really hoping that I would be able to show it to you here, but it's not working. So try this out. Here, for metallic materials, it's really difficult to measure the temperature of the object itself, because you are always getting the reflection. So this material has a low emissivity. It's stainless steel, but also the same behavior is for the aluminium, copper, and basically all metals. So if you want to measure the temperature of such shiny objects, then it's quite hard to do that. And one way to do it is to glue special stickers on the object itself. And those stickers have defined emissivity. So I know the emissivity of this object. This is 0.96 for this particular sticker. And only at this sticker I could measure the real temperature of this sheet. On all other places, I get the reflection, and I will definitely not measure the temperature correctly. So, try this. I'll pass you also the other materials so that you can try it out yourself. And I'll pass you also the stickers that are used to cover the object. So, by the way, this is the glass. And I'll pass you also this. Well, probably it's just a can filled with water. But here you can try yourself what are the effects of emissivity. Here, if you look on the can from one side, it has a different emissivity than from the other side, because I simply glued some scotch tape on top of it. And you will see it has a really huge influence on what you measure. The difference can be really big. It could be like 50 centigrades. So it is very important that you know the emissivity of the object. Okay, so unfortunately no demonstration with this thermal camera, but let's see, I could also pass it to you from the other side so that you have more time to play. So try this out, and let's say I'll take some of those materials so that you can play yourselves with that. Okay, so applications of total radiation pyrometers are that we can measure temperatures without contact with the object. So let's imagine you have to measure some temperature of an explosion. So during this explosion you can measure the temperature. So that's an example here, explosion, and this is the thermometer, well, pyrometer used for this application. Something more in the engineering field. For example, if you want to measure temperature of glass that you produce, then it looks like this, molten glass. You cannot really have a contact temperature submerged into that. The same for metals. If you're rolling steel, rolling aluminium, then you want to have information about the temperature, and this allows you to do that. So here you see some examples of the pyrometers that are used in this application. So this is the device. This is the device. I have some video showing what are the application examples. So let's take a look on the first one, for example. So those are some industrial pictures of non-contact thermometers. Doesn't have any sound, but just to see the devices. Also, they don't say what applications this is, but here you see the non-contact thermometer. So this looks like a furnace. So it's over here, the pyrometer. Or maybe there's another video that's quite interesting. It's also with sound. So let's take a look. So here you see non-contact measurement of float glass lines. So the glass is produced here in a furnace. It's being floated on a thin bath that's molten, and here you see the sensors that are installed in this furnace. So here we measure the temperature inside the furnace, inside the multiple zones, so that we have the correct temperature. Since the temperature is really high, the radiation is guided through a fiber optic cable. So here you see we have multiple fiber optic sensors. We measure the temperature between the melting furnace and between the floating furnace. Two-wire sensor, it could have a current or voltage output. So then you can see it over here at multiple places installed, and then the glass gradually cools down. This is a line scanner. It measures temperature in a line. So here I have later a video. It measures the temperature at multiple zones when the glass is cooling down. So you continuously pull out the, well, let's say here, just to show you the process of how glass is made. I'm not sure if, yeah, it has some sound. So it's a really large oven. You continuously need to monitor temperature in the process, because if the temperature is not okay, then the glass will break and it will not work correctly. So it's the furnace where we measure the temperature and gradually it cools down, and now it's being pulled out over a thin bed, and that's the reason why it's so flat, and we need to monitor temperature continuously during this process. That's an example where you can find non-contact thermometers, because there's really no other way how to measure the temperature in this kind of application. So you see now it gradually cools down, and now at the end it's cut into sheets of glass. Okay, so let's go to IR thermometers. IR thermometers are the simple way how you can measure temperature. We have a detector that's inside of this thermometer. This detector is either a thermocouple or a bolometer, which I will show you in a few minutes when we will be talking about thermal cameras. So here we have the radiation from the object. We have a lens, and this lens focuses the radiation on the detector. So here we measure the temperature with a thermometer. When you work with infrared thermometers, then it's quite important to use them correctly. we always need to keep in mind that the information that we get is radiation, it's not temperature. And that we have always the sum of emitted radiation, reflected radiation, ambient radiation, and so forth. So here I have two examples of infrared thermometers. Let's say a more a smaller one, cheaper one, and a bigger one, better one. But with all devices like this, you need to keep in mind that we are receiving the emitted radiation. The infrared thermometer has always some field of view, so it's not measuring in a single point, it measures in an area. So here you have an example. This is an infrared thermometer, and this is the field of view. So it's always this area where we measure. I can show it to you here. This thermometer, for example, is showing you the field of view with those three dots. The dots in the middle, the dot in the middle is showing me the center of this area, and the dot over here and over here is marking a circle where this is measuring. So, for example, if I would do this, then I would, okay, I'm measuring the temperature on the wood. Here, I'm measuring the temperature on the wall, but here, I'm measuring the temperature somewhere between that. So here I see right now it's showing me 23.7. Here it's showing me 24.4. So it's a different temperature. But the reason for that is that I have a different emissivity. There is a different emissivity on the wall, and there is a different emissivity on the wood here. So even if the temperature would be the same, I would see a different reading because I need to adjust the emissivity. One way how to achieve the correct measurement we already know. It's just to place the sticker on the specific point. So if I would like to measure the temperature correctly, I need to place the sticker on the object, and then I need to adjust the setting of the IR thermometer to have the same emissivity. It is possible to adjust emissivity on some IR thermometers like this one. You can change the emissivity. Here, this cheap device that does not have any possibility to change emissivity. It's set to a fixed value of 0.95. So if I would measure emissivity with this, or measure temperature with this thermometer, I will have false readings because I don't have the correct emissivity. Another way how you can change the emissivity of a surface is to paint that with a special paint. So there are paints available like this, and they have defined emissivity. So this one has also emissivity of 0.95. So you spray the surface where you measure. This one is black, and it gives you a defined emissivity on the entire surface. So that's emissivity. That's one problem with IR thermometers. Another problem is that the field of view needs to be completely covered by the object itself. So here, this is wrong. So here, if I have the object that is smaller than the field of view, then I have radiation coming from the object, and I have radiation coming from the background. So here I will see the temperature that is not correct. The ideal way is that your object is larger than the field of view, and that you cover completely the field of view with the object. So this is quite important. You can also try it out with the IR thermometer. Point that on some object, and then if you would point that, for example, here somewhere, and on the wall behind that, then you would see that it gives us different readings. Another thing is that the field of view, as due to the optics, gets larger if you're increasing the distance from the object. So here we have distance d, and this diameter of the field of view, this is given always in the manual of the IR thermometer. Typically, it's a value of something like 6 to 1, 5 to 1, roughly like that. So if you are in a distance of 6 meters, then this would give you 1 meter diameter. You can use different optics to change that, but this is the typical ratio. Here you have data from the small IR thermometer, just to give you the accuracy that you may expect from these devices. So accuracy, well, roughly plus minus 1 centigrade. Well, this is in Fahrenheit, so a little bit smaller. So let's say you can expect accuracy of 0.5 centigrades, something in this range. However, if you do not set the emissivity correctly, you will get completely different readings. We'll have some experiment on the lab as well. Okay, so thermocameras. Inside of the thermocamera, there is a sensor that is called a bolometer. You can imagine a bolometer is something similar to a temperature sensor. We've been talking last week about contact temperature sensors, and I showed you RTDs, so resistive temperature detectors, and this is something similar. Inside a bolometer, there is a layer that is changing its electrical resistance with temperature. The changes are very small, but we can detect that. So this is the sensitive element. This is like an RTD. And since the temperature changes are very, very small, then we need some insulation from the bottom here. So this is there is a reflective layer to prevent radiation coming into the backing material. And those legs are used as terminals so that we can detect the changes in resistivity. This is a single element. It's a single pixel. But inside, since we want to get a thermal image, then we need a matrix, a quite large matrix of several hundreds, thousand of those components. So here you have my electron microscope picture of such a bolometer. So here those are the pixels. You see the size. This is roughly 10 micrometers. So let's say 30 by 30 micrometers is the size of the pixel in this detector. And the whole bolometer is then arranged on a chip. And here we see that's the optics from the materials, germanium lenses. And here this is the bolometer, and it's acting like a CCD chip in a camera. The difference is that here we detect infrared radiation. With a CCD chip, we detect visible light. Here are some chips, bolometer arrays. So this is the chip itself, mounted on the electronic boards. This is just the bolometer, and this is then the lens made from silicon, from germanium, and the chip is behind this lens. The thermal camera, so you have a chance to play with that. I'd like to show you the correct way how to work with a thermal camera. We always need to remember that we are not measuring temperature, but we are measuring radiation. So first of all, we need to set emissivity correctly. And then, so this is an example here. Here you see an object which has the same temperature, but since the emissivity of different part on this object is different, it looks like it has a different temperature. So here you see it looks like there is a higher temperature here. It looks like there is a lower temperature here. This was metal, and this was snow. It was in the winter, and this is wood. So all the materials have different emissivity, and it appears to have quite different temperatures, but in fact it does not have different temperature. How you can verify that? Some temperature sensors, especially infrared thermometers, they have a connector for this thing. This is a thermocouple contact probe. And hold on, I'll take a different one. So let's say I will use this one. If you want to verify your reading, you can connect this sensor. This is a thermocouple. This is type K, and there is a connector on the thermometer. You plug it in, you verify what's the temperature, and you eventually adjust the emissivity on the thermometer to match the reading of the contact sensor. So by this way, you can go around the object, you can verify that your temperature reading is okay, and this will be then valid on the material with the same surface. So this is also one way how to set the emissivity correctly, because if we don't have any data about the emissivity, and we simply cannot use the IR camera or thermometer to read the temperature. If, for example, I would like to measure temperature of this black board, okay, I can safely assume that it has the same emissivity at the whole surface. Then a thermal camera can give me the relative temperature. If I do this, then well, if you have a thermal camera somewhere, try now to point it on my hand with the with the thermal camera. Where's the thermal camera? And where's the second one? Yeah, so point it now on me. And the second one, take it as well. Take the second thermal camera, please. With a battery? Okay, so now you should see an imprint of my hand on the blackboard. But so you see it? Okay, so it was somewhere around here. You cannot read the temperature from the wall, from the blackboard, simply because you don't know the emissivity. So now I could either spray it all black with this special color, or I could put the sticker on it, and I could adjust the temperature and emissivity, or I could take this probe. I could verify what's the absolute temperature at one point, and I can adjust the emissivity so that it corresponds to the temperature that I read correctly. We'll have a lab exercise related to that. Second thing is reflections. Here you see it's me in front of the mirror. So if you have a reflective object, then you can't measure the temperature of the object, but you measure the temperature of the object that you temperature of the mirror. Here you see that's my reflection, and I could only measure temperature on some of the points here, but it would not be the temperature of the mirror or temperature from my body. So if you have shining objects, then you need to go around the object to see if this really is a reflection or if it's coming from the object itself. Okay, example applications. What can you do with a thermal camera? We can see sediments in tanks, for example. Hold on. Přijďte za 5 minut, jo, já skončím dřív, protože to nefungovalo spousta věcí. Jo. Okay, so here that's an example of a tank. We see some liquid inside the tank, and if there are sediments on the bottom, we can see it over here simply because the temperature on the surface of the tank is a little bit smaller, and we can see that this is a sediment. We can detect problems in electric machines, for example. So here you have an image of a motor. There is a bearing here, and when the bearing is overheating, we can see that as a higher temperature over here. If we don't know the emissivity of the surface, there's nothing we can say about the absolute temperature. We can just say, okay, it's warmer here, it's colder over there. That's all we can say. We can detect leakage under some insulation. So here you see there's a pipe, and if there is some leakage under the insulation, then we can see, okay, here it's a little bit warmer, and this can be detected. Thermal cameras are very sensitive. They can detect very small changes in temperature. So if you have a field of view, then you can easily detect like 0.05 centigrade. So very small changes. You've seen here also with this example on the blackboard. We can detect problems in electronics. So that's an image of a printed circuit board. This is some chip, this is another chip, and you see, okay, here it's warmer, here it's colder, so there probably is some problem with this circuit, either short connection or some faulty chip and so on. Again, we can't say anything about the absolute temperature. We can say, okay, this is warmer, this is colder. That's all. If I would really like to read the absolute temperature, we would need to spray paint this with this paint, and then we say, okay, this is the correct temperature reading. One interesting application that was one bachelor student that was working with me. He was working on a way how to measure without the contact the temperature of these brakes in a racing car. So here you see that's the brake. It was a truck, and this is the temperature sensor that was measuring the brake. I found a similar application also for a Formula student. It looks quite nice, but here we had a problem with the absorption of the radiation. Here it was okay, but here the problem is that during some stages of the race, the brake was water cooled. So they were spraying water directly on the disc to cool it faster down, and at this moment there was water vapor all around it, and in those 3 centimeters distance, the radiation was completely blocked by the water vapor. So this was working fine until they started spraying water on the disc to cool it down. So all this needs to be taken into consideration when you measure without contact the readings. This is the data from the sensor. So I think this was a thermocouple. This was the IR thermometer. So it looks like similar values were obtained. I recommend you to take a look on those applications. So non-contact measurements in glass production. For glass, you have the problem that it has a low emissivity. So you see the reflections and you see the objects that are behind that. But there are ways, let's say optical ways with optics to eliminate this. You measure on a single wavelength. So those two videos explains quite nicely how this is done. Any questions so far? Okay.